All right, so these are the solution sets to the quiz that you just took. I am streaming this live on Twitch, but this is mostly intended for recording and posting on YouTube. The first problem, you have Toby, who is an orange cat, who is up on top of a shelf. So here's Toby. He's kind of cute. His eyeballs, nose, and a mouth. And Toby's mommy is lying down on the floor and throws Toby's favorite toy, a little soccer ball. She's a lot of favorite toys. That goes up and then back down. So this starting velocity going upward was 6.5 meters per second, although we change it later in the problem. So the question that you're trying to figure out is, how long does Toby have to grab the toy as it flies past her? So we want to know how much time that part of the motion takes when the toy is above the level of the shelf. And we'll start our work kind of to guide us. We can draw position, velocity, acceleration graphs. So to do those, let me construct some coordinate axes here. So first we'll do acceleration versus time. Actually, I don't want to put my axis label there. We'll put our axis label here. We'll do velocity as a function of time. Oh, I just realized that that is not showing up so well in the recording. I'm going to adjust my lighting. We'll do that. And I'll look at the camera. We'll do that. Hopefully that will show up a bit better. Or I could just change colors. We'll change colors. Sorry about that. We'll make these graphs be pink, and then they will show up better. This is the problem with doing physics live. Sometimes you grab the wrong color chalk. I have tons of this red chalk, and it doesn't show up in camera very well. It's time. This is acceleration. And we know position can't go below 0. So the position, we'll use y here. You could use x. Will be there. And we're going to choose this line down here to be our origin of coordinates. Now I'm going to start and go from top to bottom. The toy is always in free fall, so the acceleration will always be negative g. From the moment it leaves Toby's mommy's hand to when it falls back to the floor, its acceleration is negative g. The velocity starts positive at v naught and goes down. In this graph, the slope here is minus g. You know that the slope of the velocity curve is the value of the acceleration curve. So a constant negative acceleration gives you a constant negative slope. And, well, this goes up into the air and comes back down. We know that a graph with a slope that begins positive starts to go up and then ends negative, then goes down. This point here is the apex of the thing's motion. So it goes up and then back down. And we should indicate the level of the shelf on our graph. We don't know exactly where it is yet. That's fine. We're going to do some mathematics to find it. Is right about there. So what we want, the thing we seek for this problem, is we seek to know this time interval, that amount of time. Right? So there's some time here when the height goes above the shelf, and then sometime later when the toy goes below the shelf. We want to know the difference between those. So the question, right, the way you phrase the thing you're trying to do in words, then takes this form. What is the difference between the two times that y equals h? Now, 90% of you put the numbers in by this point in solving this problem. I'm not going to do that. I don't like numbers because they make me break out in calculators, and I don't like calculators. If you put the numbers in already, this is fine for you. I'm going to do it my way on the blackboard. You can do it however you like, solving problems on your own. So we're going to write down an expression for y of t. We in fact don't need the velocity. It's pretty irrelevant to the problem. So here we know y of t is, well, it's going to be 1/2 at squared plus v naught t plus y naught. But the initial height is 0. We know these other two things. We know the acceleration is minus g. So that means that the position as a function of time, y of t, is minus 1/2 gt squared plus v naught t. So I'm going to set this thing equal to the height. So what I have here, I'm just debating how I want to color code this. I have h equals that equation, minus 1/2 gt squared plus v naught t. So h here is the level of the shelf, and this is the position of the ball. So I know that, again, my graph guides me to this. There are 2 points in which the ball goes over the shelf, and what I seek is the difference between them. Now, if you have experience with algebra, you probably already know how this is going to go. This is a quadratic equation. Quadratic equations have 2 roots. So let's solve this equation. So we do quadratics by putting everything on one side, setting the equation equal to 0. So I'm going to put everything on the left-hand side. I'm going to color code again. So 1/2 g, let's see, I can use pink, 1/2 gt squared minus v naught t plus h all equals 0. So I've got the quadratic formula that I know. I know this is A, this is B, and this is C. So the quadratic formula tells me that the value of the time is, let's see, it's minus B, so I have V naught plus or minus the square root of B squared, so V naught squared, minus 4AC, so minus 4 times 1/2 g times c, so the 4 turns the 1/2 into a 2, so I get 2gh. 2gh. All of that is divided by 2a. Well, a is 1/2 g, so all of that is divided by g. Now, at this point, I should put in the numbers. Right? All that's left is to do the calculating. I'm going to use g of 10 meters per second squared. So this gives me t equals so v naught here is 6.5 meters per second squared. 6.5 meters per second squared plus or minus the square root of, so I have 6.5 meters per second, 6.5 meters per second plus or minus square root of this. So I have to use a computer to square 6.5. I don't want to do that in my head. It's 4,000 something, or excuse me, 40 something. So this gives me 42.25 meters squared per second squared minus 2gh. I'm going to use g for 10, or g as 10. So this is 2 times 10 meters per second squared times 2 meters. So notice I get again units of meters squared per second squared, the square root of which is meters per second. So all of my units are coming out in the way that I want them to. So this gives me minus 40 meters squared per second squared. And all of that is divided by g, which is 10 meters per second squared. It's always a good idea to carry your units around because you can use them to make sure that what you've done is correct. Notice, I have meters per second plus or minus the square root of meters squared per second squared. So the numerator all matches. And then I have meters per second divided by meters per second squared, which gives me something in seconds, but I'm looking for times. So that is what I want. So I'm going to, I could do this in my head. So let's see. 42.25 minus 40 is 2.25. The square root of 2.25 is 1.5. So I have 6.5 plus or minus 1.5 is, let's see, I get 5 and 8 divided by 10. So this gives me times of 0.5 seconds and 0.8 seconds. All right? But what we wanted was the distance between them. So this value right here, draw a little dotted line. This is t equals 0.5 seconds. This one is t equals 0.8 seconds. And the distance between them, the thing that the problem asked us to find, the whole point of this, how long Toby has to grab her favorite toy out of the air, is 0.3 seconds. That was what we came here to find. Now, I did this likely in a way that is different than what many of you did. In that I didn't put in the numbers. If you said, all right, I've got this, let me shove in the numbers right away and do the quadratic formula right away, that's fine. You get full credit for doing that. But I wanted to kind of model for you preserving the algebra as long as possible. And then when you put in the numbers, put in the units as well, because that lets you verify what you've done. Now, the last part of the problem asked you to imagine that Toby's mom didn't throw the ball quite as hard. But since I've done this entirely with variables, this is exactly the same, I just have a different initial velocity. So what I'm going to do is I'm going to step back and let everybody take a look at this, but I'm going to just erase the graph because that will change, and I'm going to erase the thing with the numbers and just put in different numbers. So my graph goes away. Get rid of this part. and the thing with the numbers goes away. So now all I'm going to do is put in different numbers. So here, t equals, let's see, the initial velocity now I believe was 5 meters per second. So I have 5 meters per second plus or minus the square root of, let's see, 5 squared is 25, so 25 meters squared per second squared minus 2gh, which is 40 meters squared per second squared. You're probably already screaming at me about what's going to happen next. Yes, I know, I just want to finish this. Divided by g is 10 meters per second squared. What happened? This is imaginary, right? So what does it mean? Well, remember that the quadratic formula tells you where parabolas intersect lines. So we went to the quadratic formula seeking to find where a certain parabola intersected a certain line, and we learned that if Toby's mom throws the ball at 5 meters per second, that it doesn't reach the shelf. And Toby is sad because she never gets to see her toy. So that is problem 1. I hope this is useful. I'm just adjusting the camera. Give me a little more room for problem 2. So what are the skills that we had here? Kind of like to do a recap and say, what did we learn from here? So we saw that, first of all, a cartoon is very helpful if us understand what's going on. We needed the equation of motion. So this is the general case. This is the specific case for this problem, where we knew that the acceleration was minus g, and the initial height was 0. Drawing acceleration, velocity, and position graphs can help us understand how things are moving. They kind of guided us, at least in the first part, to looking for intercepts between the motion of the ball and the location of the shelf. And we saw, for instance, that the value we wanted was the distance between these two, right? And then all that's left is to find that distance. And once we have that in mind, once we understand how this is going to come out, that we're going to have an equation with 2 answers, this gives us confidence that we're doing the right algebra. That you say, okay, let me set position versus time equal to height. So here it is. Hey, this is a quadratic equation. Those have 2 answers. So, hey, look, all right, everything is going to make sense. And then I know that many of you have kind of been trained in grade school to say, oh, I got an imaginary answer. I must have done something wrong. No, an imaginary answer just means that these things have no intercept. Toby can only imagine her favorite toy. So I'm going to stop the recording here, and then I'm going to right away record problem 2.